Hello, and in this final video from section 5.8, we're going to cover logistic models. Logistic models are a little bit different than exponential or exponential model in that they have a limiting factor. So a logistic model is used when we have a restriction on the population. That means an example of this would be like if you were populating a state, that means you have a restricted amount of area and resources. Then your carrying capacity, or C, that's the maximum population that can occur on that part of the state, I guess is what we're saying here. So if we, for example, another example would be as if we had an island, how many birds can populate that island. That would be a carrying capacity, C, would be a limiting factor. We can only have so many, and then their resources would run out. Well, this is the equation for a logistic model like this. It's y equals c over 1 plus a e to the minus bx. C is the carrying capacity. That's the maximum value that can occur. A is found by subtracting from the carrying capacity the initial value and then dividing by the initial value. And B is going to be the growth rate that's going to occur there. Now this is minus B, so it's just going to be the opposite. So growth rate is going to be the opposite of that decimal there. So here's the example on your worksheet. It says P of T equals 20,000 for 1 plus 7 e to the negative 0.1011 t. Models the population of deer in a game park. In this model, T equals 0 represents the year 2010. What's the population in 2010 and 2012? According to this model, what year will the population reach 10,000 deer, and what seems to be the limiting size of the herd of the deer? So I've already told you the limiting size, so we can answer C right away because the limiting factor is this value right here. So the limiting size is going to be 20,000 deer. Is going to be our limit for C. Now we can use this model, and for part A we can plug in some values. For 2010, that's the beginning year, that's when, so 2010 is going to be T equals 0, and 2012 T is going to equal 2. So we can just plug those values in to the equation and find out the answers. All right, so to get 0, that should be an easy one to evaluate because anything to the 0 power is 1. So this is going to be, for this value right here, I can do that probably with a less calculator than most times. So I got 20,000 over 1 plus 7 e to the negative 0.1011 times 0. Well, all of this right here is going to equal 1 because that's all to the 0 power. So my answer is going to be here 20,000 divided by 1 plus 7, or 20,000 divided by 8. So we could just turn on my calculator and do 20,000 divided by 8. So my population is going to be 2,500 at the start at 2010. So P of 0 equals 2,500 deer. So we start at 2,500 deer and then move our way up. Now for this one, T equals 2, I'm going to have to do some more. I'm going to have to do more calculator stuff on that one because I don't know the power. I won't know e to that power there. We're just going to put it in and evaluate on our calculator. 20,000 over 1 plus 7 e to the negative 0.1011 times 2. Alright, let's plug that into our calculator and see how many deer that approximately we have. So I need to make sure I use parentheses if I'm typing it all in at the same time. Parentheses 1 plus 7 times e to the power of negative 0.1011 times 2. In the parentheses for the power, and then in the parentheses for the denominator. Alright, so on that one we're going to have about 2,976 deer. 976 deer. We can't have a partial amount of deer. Alright, and then our last question here is, when will it reach 100,000? That's half the carrying capacity. We're going to start out 2,500. We want to know when it reaches 100,000, or I'm sorry, 10,000. Comma's missing. So in that case, this is C. In that case, we would solve the equation. We'd put 100,000 or 10,000 in, and we would solve it for T. Okay, so we put in 100,000. First thing we need to do is multiply by the denominator, or you could think of it as cross multiplying. If you put a denominator here of 1, we can cross multiply across. Either way, if we multiply by the denominator, 1 plus 7 e to the negative 0.1011 t on this side and on this side, we would then get this side over here would reduce out and just leave us 20,000. So the right hand side here would be 20,000. Okay, the left hand side would be 10,000 times this, so that would be 10,000. We do distributive property here. We multiply 1 times that, we multiply 7 times that. So we got 10,000 plus 7,000, or 10,000 plus 70,000 e to the negative 0.1011 t. Now we need to subtract and divide first. So we're going to subtract off our 10,000 from both sides. We get 70,000 e to the negative 0.1011 t equals 10,000, and we divide by 70,000, and that's going to give us the next step would be e to the negative 0.1011 t equals 1/7 reduced. Then we apply the natural logarithm of both sides because it's e. And then since these are inverse functions, we're going to get negative 0.111011 t equals ln of 1/7. And we have to divide to get our answer. So t is going to be ln of 1/7 divided by negative 0.1011. And that's approximately 19.24. 25, if we round up. 19.25, and we were answering a question in what time unit? What year? So basically 19 years after 2010. So we're going to have to add 2010 to that. So that's going to be 2020. 29. So sometime in the year 2029, quarter of the way through it, we're going to have our population being 100,000 deer. Now we could probably solve this quicker or more readily on the calculator if we had the window set right. So we can verify this on the calculator by just taking this and plugging it in and doing our intersection, right? That's what I'm saying. 1 plus 7, 1 plus 7 e to the power of negative 0.1011 x parentheses, and we want to know when it's 100,000. Okay, so we have these two formulas. Let's take a look at what they look like. So our maximum capacity here, so we're going to go out to be like 100 years, and we'll go by 10. Our maximum capacity though was 20,000, so I'm going to go up to 20,000. 2, 3, and we'll go by 5,000 here. Oops, 5,000. And we'll push graph. So here's what the curve looks like. So this is what the logistic model looks like. It goes here. It starts at 2,500. It curves up, and it has a limiting factor of 20,000. So it gets really close to 20,000, but doesn't ever meet at 20,000. This line's halfway in between, so this would be the year that we would do that. But it always looks like this. It curves up and has two asymptotes. One asymptote at the carrying capacity and one asymptote at the x-axis. It'll continue to curve down, and it will be at the x-axis asymptote. So it has two asymptotes, and it always looks like this, or it drops down if we're decaying or losing population, where b is going to be a negative number. Actually, in the problem, it would be a positive value there. Would be decreasing population, because in the formula negative b goes here. So a negative would be a positive. All right, let's do our intersect here and make sure that we have the correct answer of correct guess. We're guessing it's over here because that's where it looks like it crosses. We're hoping it's at 20. It's at 19.24. Is that what we got? Yes, it is 19.25. Actually, it's 19.247, so it did round up like we did. So it gave us the same solution that we did algebraically. So that's what a logistic curve is, and it's used to model things that have a carrying capacity. So something that has a maximum population or a limiting factor on the population. The other ones have unlimiting factors. It continues to grow at an unlimiting rate. Okay, so that's what logistic models do. So if you have a couple problems on that on your homework, now you have a formula and what goes in the formula.